Okay, we're gonna continue on here, chapter 11, and then whatever's left, chapter 17, and our final weeks here together. All right, so in chapter 11, obviously the main focus last time was electron configuration. And remember, electron configuration basically tells you how the electrons are distributed within the atom. Remember that essentially electrons will go into the atom lowest energy level first, and then will continue to fill, higher energy levels and higher orbitals and so forth. And there's a couple important things that we talked about in terms of electron configuration. Obviously, the orbitals, which are again these theoretical sort of locations of where we find electrons within the atom. Again, there are s orbitals, and s orbitals, there's only really one type of s orbital, and s orbitals begin on the first energy level, and they appear on all the other energy levels as well. And in terms of maximum electrons that you can fill in an s orbital on any sort of level is 2 electrons. Remember that any individual orbital could hold a maximum of 2 electrons. They don't necessarily have to be full, but that is the maximum that you can kind of put into an orbital. There are p orbitals, and in terms of p orbitals, there are 3 different types of p orbitals, px, py, and pz, which are sort of the orientation in 3-dimensional space. And they don't begin until the second energy level. So that is, again, where they begin. It's the second energy level. And from the second energy level on, you'll find some p orbitals. Now, in terms of p orbitals, if you were to fill up all 3 of the p orbitals on any energy level, which is sometimes referred to as a subshell or sublevel, you could put 6 electrons in there. D orbitals, there are 5 different types of d orbitals, and it's not until that third energy level that we really do see d orbitals start to appear. Same idea here, since there are 5 different types of d orbitals, you could get a maximum of 10 electrons in there on any energy level, and once again, that would be if you fill the entire d subshell. F, there are 7 different types of f orbitals. They start to appear on the fourth energy level. And if you filled up 7 times 2 is 14 if you put an electron in each of the orbitals. So knowing, again, the maximum number of electrons that you can put into a particular orbital or subshell is really important for writing electron configuration. And as we talked about as well, you can also use this sort of feature here to help you figure out the proper order at which electrons go into the atom. Again, as we talked about here, you can really just start with like the 1s. Then you can just kind of go over to the right and go 2p, over to the right 3d, over to the right there 4f. And really at that point, you can just kind of fill in the numbers underneath. If you don't run out of room like I did here, but you can throw a 7 down there at the end. And then we go 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And this will give you, again, the proper order. And as we've talked about last time, we always start up on top, and then we just kind of zigzag back. And really the main difference where people oftentimes will screw up is right around here. The 4s does again come before the 3d. It is lower in energy, so it does get the electrons first. And that pattern does follow as you continue on here. As you can see, you'll hit the 5s before you hit the 4d as well. So if you know pretty much this and you know how to create that, you pretty much can write any type of electron configuration that you would need to do. And remember, if you had something like we looked at, like say, we didn't look at aluminum, for example, 13. Again, we would start up here at top. It would be 1s2. Then we zigzag back to 2s2, 2p6, 3s2, and 3p1. Once again, this is how we properly write electron configuration. First number is the principal quantum number, which is that n number. This is the orbital or subshell that the electrons are in, and the number on top is the number of electrons in an orbital or subshell. Now, remember, this is the way we do it. No, as I mentioned before, no commas, no dashes, no things like that. So again, kind of a regular size number, lowercase letter, and superscript number there for the number of electrons. You count up the top numbers, it tells you how many electrons you put in there. And also this gives you an idea in terms of where the electrons are in terms of energy. We can see on the third energy level here, which is all these guys that have threes. There are 3 electrons on that energy level. Here on the second energy level, which is all these guys that have 2s, we have 8 electrons, and on the first energy level, obviously, we have just the 2 electrons that are there in the s. We also talked about that you could draw what is sometimes referred to as the orbital diagram. An orbital diagram is either boxes or lines to represent the orbitals. If you were going to do it properly with energy, you want to go kind of left to right like I'm doing here, you would go upwards. But just to save space, we will go left to right here. And as the electrons go in, remember the first one always goes upwards, and Pauli's exclusion rule tells us that whenever we have 2 electrons in the same orbital, they do have to go in opposite directions, which is referred to as being paired spin. Same thing would happen here. When we get to a set of orbitals that is in a subshell or sublevel, Hund's rule tells us the most stable arrangement is maximizing parallel spin, which means that they will actually go in one at a time first into those orbitals. When there's no more room, basically, they will then be forced to come back through and pair up. So that's always sort of how those electrons go in to a subshell that has multiple orbitals. Again, all the way up. And then you would come back down. In this case, suppose doing aluminum. I got a little overzealous there with the aluminum there. We'll get rid of our electrons. Look like that there. Any questions on any of that stuff we talked about there last time? All right, let's see. We left off somewhere. I think we left off that you can use the periodic table to sort of count off electron configuration, as when we look at the periodic table, the first 2 groups again are the S block, is sometimes referred to. So this is referred to as the S block. And as we know, S can hold 2 electrons, so that's basically what that means, 1 and 2. Groups 3 through 8 are pretty much the P block here. And P subshell could hold 6, so 1, 2, 3, 4, 5, and 6. And our D, which is really our transition metals here, are found here, our D block. And it could hold 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And down here is really our F block. And they could hold 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So if you know what you're doing, you can just literally count it off as we just did aluminum, which is right about there. And again, if we were going to count it off, we would do, this would be 1s2 to here. This would be 2s2, 2p6, 3s2, and 3p1 right there is basically how you can count it off. Now, we also talked about if you were to choose to do that, you do have to be careful. Again, if we look at our friend iron, which is somewhere in this ballpark there. We do have to remember that that is 3s2. So we go 1s2, 2s2, 2p6, 3s2. Here we would go 3p6. This is 4s2. A reminder that this, though, is the D's, and it does start at 3. So this is technically not 4D. even though it's on the fourth period, is one behind. It is 3D 1, 2, 3, 4, 5, and 6 in this particular case. So that's really important. The other place is important is down here, because the F start on the 4, that would be 4F, that row, that would be 5F. Again, they go right about there, which is actually 2 behind the period number. So when you get to the F's, they're actually 2 behind the period number. So there's a little kind of weirdness that happens as you kind of get in that middle section. If you're trying to kind of count it off, again, I would recommend using kind of the zigzag guy, and you should be okay. Now, we also talked about really 2 exceptions last time, which is copper and chromium, and that's 24 and 29 on the periodic table. And again, the exception is that at the end, if we were looking again at something like chromium, 1s2, 2s2, 2p6, 3s2, 3p6. And if you were following that sort of chart thing that we normally do, you would go 4s2, 3d4. Now, a couple of things we talked about as well. If we went up to the configuration up until this point, that is 18, which is argon, which is sort of a shorthand you could also do when you're writing electron configuration. You could go, that is argon. It does need to be a noble gas that goes into those parentheses, and that's the noble gas that comes right before, obviously, what we're writing electron configuration for. The exception is it actually has one less electron in the S and one more electron in the D, so the proper configuration would be 4s1, 3d5, and that would be for chromium. And copper has a very similar sort of exception, argon 4s1, 3d10, rather than 4s2, 3d9. Yes. You should know how to do it, but I don't know. That's a lot of electrons. So, but yes, it's possible. I'll say it's possible. Yeah. Probably we don't use typically in chemistry too much in that area, but it is possible. You should know how to still write the configuration for it. Other question? All right. The other thing we also talked about was, and you're not going to be responsible for it in this class, which is this is like where chromium is, and then copper is right around here. It's copper. Again, if you do sort of go down and in below those 2 on the periodic table, there's a number of those type of exceptions that do occur. But for us and most chemistry classes you take, chromium and copper are kind of the 2 main ones that they want you to remember. But we saw things like silver have an exception. Things like PD has, for example, no electrons in the S. They've all been kind of promoted up to D. So there's a number of exceptions on the periodic table below those 2, and kind of down and in, you'll find similar types of exceptions. Now, speaking of those transition metals, one of the reasons that it's not that sort of super impossible in terms of energy wise, why maybe an electron might sort of move one energy level or the next, is these 2 energy levels here, when we talk about sort of the 4s and the 3d, they're very close in energy to begin with. And as the electron is sort of filling with, or the atom is filling with electrons, as we talked about, the 4s is really lower in energy and the 3d is higher. Once we start sort of, again, populating the electrons into the d orbital, there's this sort of switch in energy that occurs. And what ends up happening is the 4s actually ends up being higher in energy than the 3d. And that's going to be really important in terms of sort of what happens when, for example, something like transition metals lose energy or lose electrons. When elements sort of lose electrons, they typically always lose the highest energy electrons, and those are really the valence electrons, and those are the ones that are typically lost. So if we look at something like, say, look at magnesium, which is 12, And if we look at magnesium, it is 1s2, 2s2, 2p6, 3s2. Now, as we know, magnesium forms a +2 charge as it is group number 2. And that means that when it is a +2 charge, it should only have 10 electrons. And when we think about the electrons that are going to be lost here, that is on the first energy level. Those are on the second energy level. And right here, these are really the valence electrons. And those are on the highest energy level. And those are the two that's going to actually lose. And that will give us 1s2, 2s2, 2p6 as the electron configuration for magnesium with a +2 charge. And that is the same electron configuration as our friend neon in this particular case. And one of the things that we talked about when we talked about nomenclature and we talked about really bonding as well is the idea that really the whole purpose of bonding is for everybody to achieve that noble gas configuration in terms of electrons. And that's what we see here when we do see ions being formed. Again, in ionic compounds, that's achieved by transferring those electrons from the metal to the nonmetal. In covalent bonding, that's sort of achieved by sharing electrons, right? To kind of get to that same electron configuration. Remember that magnesium and neon are what are referred to as being isoelectronic with each other. They have the same electron configuration, basically. If we looked at oxygen, again with no charge, has 8, and it would be 1s2, 2s2, 2p4. Oxygen, which is group 6, we know makes a -2 charge, which means it has gained 2 electrons. And again, it has room for those electrons in the p subshell. And that is where they will end up 1s2, 2s2, 2p6, which again is neon's configuration. So basically, neon, magnesium with a +2 charge, and the oxide ion, they're all isoelectronic with each other. They all have the same electron configuration. Any questions on that? So when we talk about sort of representative elements, when they gain and lose electrons, they will actually end up at the same electron configuration as the noble gas. So if we're talking about a metal, when it loses electrons, it will back up to the noble gas that comes right before it in terms of this electron configuration. And if we talk about a non-metal gaining electrons, it will go forward on the periodic table to the noble gas that comes after it. Remember as well that they do not become those elements because in order to do that, the protons would have to change. So they still have the same number of protons, so it's still magnesium. But in terms of their electrons, they become a very stable sort of situation with their electrons, like the noble gas. So again, they're not like becoming those elements. Just in terms of their electrons, they're becoming very similar and a very stable sort of situation. Any questions on that there? Now, with that being said, if we roll to our transition metals, they are a little bit different in terms of how they sort of lose electrons and sort of how they end up. So when we look at transition metals, as we just talked about, the 4s, for example, gets our electrons first, then our 3d. And once again, as soon as that sort of happens, we get that switch in energy, which means, as I talked about a second ago, our 4s will actually end up being higher in energy. And that means that when transition metals, which are different than the representative elements, which is basically group 1, 2, and 3 in terms of the metals, transition metals will actually lose their s electrons first because they're actually higher in energy at this point. And then if they need to, which is a little bit different than sort of representative metals, they can then also reach into their d orbitals and take out some electrons. So, for example, if we look at iron, which was 26, I believe, and if we write our electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6 in this case. Now, when something like iron, for example, loses a couple of electrons, as we know, it can become iron +2 charge here. Again, the +2 means that it has lost 2 electrons. So instead of 26 electrons, iron with a +2 charge will actually have our 24 electrons. And if I were to fill in my little diagram here and not have an extra little line there, there shouldn't be, so we'll do that. Let's see, 1, 2, 3, 4. I guess I did 5. There you go. And we'd go here 1, 2, 3, 4, 5, and 6 in this case. Now, at this point, what's going to happen is because of the switch in energy, it is actually going to be these two 4s electrons that are actually going to be lost first. So when we look at sort of electron configuration, transition metals are a little bit different than representative metals, because in representative metals, when you look at the electron configuration, it's pretty much the last thing that you wrote or the electrons you're going to remove. But here, it's actually these guys here that are going to come off first. And those are going to provide the 2 electrons that need to be lost in this case. Again, because of that switch in energy, the 4s is higher in energy, and they will be lost first. That means we will end up with 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 in this case. And again, if we count up the top there, we got 18, 24 electrons. Or if you wanted to shorthand it, once again, this part up to here is argon, and it would be 3d6. So again, is those s electrons that always get lost first when you're dealing with transition metals, and that really goes for all transition metals. They will always sort of lose those s electrons first. So if we look back at this, whoops, where'd it go? We look back here, when we're talking about our transition metals and really what's happening when they lose electrons, this is really where we're talking about starting all the way through here. It will always be these electrons here, the s electrons, that basically get lost first. And then if necessary, they will start sort of digging into the d orbitals in that particular case. So let's talk about that part. If we took iron that actually had a +3 charge, would have 23 electrons. So once again, coming back to our little chart here, we would again take off these 2 electrons here. Problem is we need 3 electrons. So at this point, we would then have to come back down and grab 1 electron off of the D in this case, and we would end up with an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5, or argon 3d5. So a couple of things that are different with transition metals, as you can see, we will sort of take those S's first, and then if necessary, go into the D's. The other thing that you also see is they don't end up back at a noble gas in this particular case. So they actually don't go all the way back to the noble gas that comes before them, because they have a long way to go to do that. They have a lot more valence electrons sort of happening, so they actually don't get there. But it does make them a little bit more of a stable-ish safe situation in this case, because they are still getting rid of those sort of higher energy electrons and making things a little bit more stable. Question on that there. So why don't you write the electron configuration here for, let's do potassium with a +1 charge. Let's do a little selenium with a -2 charge. Let's do a nickel with a +4 charge. And let's do a Mn with a +2 charge. All right, so give those a go in case you don't have a periodic table. Potassium's atomic number is 19. Selenium is 34. Nickel is 28. And Mn is 26, 25, I think, actually. T5. Okay, let's take a look. So starting with potassium, that's 19. So 1s2, 2s2, 2p6, 3s2, 3p6, and a 4s1 in this case. Now, because it is +1, it will actually have only 18 electrons, which means it is this last one here that's going to go. And that would leave us here basically 1s2, 2s2, 2p6, 3s2, 3p6, which is also obviously our same guy as argon's configuration. We take a look at selenium, which is 34. And in this case, that would be a argon if we went to 18. 4s2, a 3d10, and a 4p4 in this particular case. And -2 means that it has gained 2 electrons, which means it should end up at 36. And they are going to end up right here in our p subshell, which would get us argon 4s2, 3d10, 4p6, which actually then brings us to not argon, but it brings us to krypton in this case, as it actually gets to 36 in this particular case. As if we include the rest of this, that takes us all the way to argon. Any questions on those two there? Taking a look at nickel, which is 28. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and we're going to nickel, which is 3d8 in this case. Now, nickel here with a +4 charge means it has lost basically 4 electrons. That means it's going to actually go down to 24 in this case. That is 2 from the S that's going to be lost first. We will then need to take an additional 2 out of there. And that's going to give us there for nickel with a +4 charge. We'll use our little abbreviation here. So we're going to go argon. Again, 3d6 in this case. The 4s2, both of them go. And then 2 of the d orbitals here as well. Question on that one. Lastly, here we have Mn, which is 25. So we'll deal a little bit of what we got on the bottom there. So let's rewrite the whole thing. So for our Mn, that will be 5 right there. In this case, our Mn is going to lose 2 electrons, which means in the case of that, we are only going to take out our S's here. And that would leave us for Mn with a +2 charge. Again, argon 3d5 in this case. Yeah. Any questions on how to write electron configuration with charges? Again, you just got to adjust the number of electrons. The only kind of weird ones is like sort of the transition metals. Again, you're not going to probably take the last thing written, but the S and then into the D's if necessary. Any questions on any of that there? All right, so let's talk a little bit about just some of these trends we talked about a while back, just to officially talk about it. Obviously, we just talked about valence electrons. Valence electrons, as we know from bonding, as we talked about it with there, are the highest energy electrons. They're really the ones that are furthest away from the nucleus. They're not held as tightly. And what makes valence electrons important is they are obviously the ones that are sort of involved in bonding, right? As they are furthest away from the nucleus, they're the ones that come in contact with everybody pretty easily. Now, you could write the electron configuration like we talked about and just kind of look at it in the case, for example, here of nitrogen. That is the highest energy level, and there's 2 and 3, which gives nitrogen 5 valence electrons. So you can definitely look at the electron configuration and figure out how many valence electrons there are. Usually will be the ones at the end is the valence electrons. Obviously, a much quicker way to do it is that the number of valence electrons really does equal the group number. And as we can see there, fluorine is group 7, so it has 7 valence electrons. Chlorine as well as group 7 has 7 valence electrons. So again, if we were to look at that, that is 1s2, 2s2, 2p5. And in the case of fluorine, those are the valence electrons right there. The 5 and the 2 give us a 7. Now, that's probably the easiest way to do that. And when we look at something like transition metals, the way you could do it is also sort of equal to the group number. So for example, you know, maybe okay, we'll just use it then. We'll steal this one. So if we look at it in terms of transition metal, what group numbers we're talking about is really not the representative numbering of A, but it's just the regular old like 1 through 18 type numbering. So this would be group 1, right? Group 2, this would be 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, basically. So as we know, when transition metals lose electrons, they're going to take these two first. So that is 2. And then basically, if you add 2 plus 1 more over is 3. And this guy would have 4, 5, 6, 7. So if we look at something like iron, like we looked at before, argon, 4s2, 3d8 in this particular case, 3d6. We look at it, we could count our 2 and our 6 gives us 8 valence electrons for iron and so forth. So most of the time, you probably won't dig into all those d orbitals, electrons, but you might need to dig into some of them. So if you're sort of asked, I guess, what is the number of valence electrons for a transition metal, it will equal sort of the group number. And again, it's just the regular sort of 1 through 18 sort of numbering there, are 3 through 12, if you want to think about it that way. Again, they have the ability to do so. Will they lose all those electrons? Probably not, right? Because you never see anything like, a copper with a plus 11 charge or anything like that. So the odds are they're not going to lose those because, as we talked about, as you lose electrons, things get smaller. It gets harder to lose the additional electrons. So even with our transition metals, they do have the ability to lose a little bit more electrons, but at some point it's probably not going to be energy efficient for that to happen. Yeah. It would be in the case of, so we're only really talking about here valence electrons. If you want to kind of look at the periodic table for valence electrons, as you come back this way, it does go back to 3, 4, 5, 6, 7, and 8. Obviously, which we talked about, helium only has 2. So for valence electron, this is sort of the numbering you want to think about is 1, 2, but here we're just going to kind of keep counting to 12. But remember, as you roll back this way, it goes back to kind of the normal counting for the valence electrons. Again, it's just that middle part where the transition metal is because basically really in the case of transition metals, the s orbitals and the d orbitals are kind of in play in terms of valence electrons being highest in energy. But remember, these guys over here will kind of fall back to our normal sort of numbering in terms of valence electrons. All right, so as we talked about with a lot of our periodic trends, we did with a number of experiments, we do see that as you, for example, go down a group, especially with metals, they tend to give away their electrons a lot easier. That also is really important in terms of reactivity, right? And what we saw, for example, in the video where we looked at, I think it was lithium, sodium, potassium, and the difference in the reactivity. We saw potassium react a lot more, I think it was with water, than say lithium did. And again, that's because it's able to give away those electrons a lot easier, making it much more reactive. We also saw when we did the halogen sort of experiment where we went to different layers and things jumped from the top layer to the bottom layer. We saw that reactivity actually increased as you went up in group 7 with our halogens. And that also is because of some of these periodic trends that we talked about, that they want to gain electrons, hold on to their electrons. While everybody on the left-hand side is pretty much the opposite effect of that. They want to get rid of their electrons and really don't want to hang on to their electrons. So as we talked about, some of the important sort of periodic trends and effects are, again, something like effective nuclear charge. And a reminder that if we had something like lithium here, which is 1s2, 2s1, it's got a +3 charge from its 3 protons. It's got, in sense of the first energy level, a couple of electrons kind of flying around. Second energy level has got 1 electron flying around. And the idea of effective nuclear charge is the idea of these sort of valence electrons, these outer electrons. What is the sort of positive charge it's actually filling? And when we talk about positive and negative attraction, it does increase with the size of the charges that are being attracted to each other. So something with a +3 charge is going to be attracted much stronger than something that only has like a +1 charge, kind of pulling it in. And what we talked about here when we did that experiment, I think way back when, if we look at these electrons here, they're pretty much are the core electrons, and they're going to feel basically the full brunt of the +3 charge from the nucleus, which is going to allow them basically to be drawn in closer to the nucleus. The result of that is when we look at our valence electron out here, he experiences something that is sort of known as shielding. And what that means is he's shielded from sort of the full brunt of that positive charge from the nucleus by those lower energy electrons. They sort of get in the way of that really big positive charge. So you could actually calculate, which is known as the effective or the effective nuclear charge, sort of the charge that that outer electron is feeling based on sort of the shielding aspect of it. So we have a +3 from our protons there in our nucleus, -2 sort of shielding electrons that are lower in energy, and that gives us a +1 charge. So this outer sort of electron is only feeling like a +1 attraction to the nucleus because of that shielding that's occurring. And that means it's not going to really be drawn in as tight as those lower core electrons are. And that's why this valence electron here, right, when something like uh, lithium loses an electron, that's going to be the one that's going to be easily sort of removed because, again, it's not being held as tightly. Any questions on that there? Electrons in the same energy level don't really shield each other. It's just those guys in the higher energy levels are shielded by guys in lower energy levels. Now, another really big sort of idea or trend that affects, how things lose or gain electrons are what is known as ionization energy. And ionization energy, again, is the energy that's required to remove an electron from the gas phase of an atom. And remember, if this is a metal, it will lose an electron, and that's typically where we would see the electron be in the reaction is on the product side, like it's being given off. And it is basically the sort of periodic trend that we think about when, again, we think about cations, which are guys that lose electrons and become positively charged. Metals have really low ionization energies, and nonmetals have high ionization energies. And again, when we look at the periodic table, this is the general trend. As you go down a group, ionization energy decreases. And as you go right on the periodic table, ionization energy actually increases. And that is why, again, if we think about it, our metals, which are kind of left and down, are typically the ones that will lose electrons, and our nonmetals up or right definitely takes a lot of effort to try to remove it. As I think we've talked about previously, but just to remind, electrons actually do come off one at a time. So for example, if we're looking at something like magnesium, he would lose 1 electron first, and then that guy would lose a second electron. And then, for example, if this process was to continue, the next electron would come off and so forth. And every time an electron comes off, there is an ionization energy associated with it, when the first electron comes off, that's what's referred to as the first ionization energy. Second one is the second ionization energy, third one, third, and so forth. Now, as we talked about before, when we do lose electrons, the overall size of it all shrinks down, which means that's going to bring even the outer electrons closer to the nucleus and being held tighter, which means as you go, for example, losing the first electron to the second, to the third, to the fourth, or however many you want to try to lose, the ionization energy increases every time you do that. And at some point, it's going to get so high that it's not going to be energy efficient for that to actually occur. And in the case of magnesium, that's right about here. We know magnesium makes a +2 charge because when we look at its electron configuration, it has 2 valence electrons, which are those two. Once we get out of there, we're now going to dig into the core electrons, and energy-wise, you're probably going to see like a 10 to 12-fold increase in the amount of energy required to do that, and it really doesn't happen at that point. So this also explains why certain elements will only form certain types of charges, and those are like, for example, our representative metals in group 1, 2, and 3. They typically will only lose 1 electron, 2 electrons, or 3 electrons, because that will take you back to the noble gas, which is stable configuration to begin with, and now you're into the core electrons, which is not energy-wise efficient to try to remove those. And that's what we see on this chart. You can see for magnesium, 735 to remove the first electron. It doubles almost there to remove the second electron, and then we're going up by almost 7 times there to try to remove the third electron. And again, it just doesn't happen. You can see with aluminum, it's even a greater sort of jump-ish almost, or a similar one. We go from 2,700 after the third electron, which is the last valence electron, to almost, 12,000 or 11,000 or so. And that's a very big jump in energy. So it's not going to allow it to sort of lose those electrons. So you can see this line kind of coming down here is where we kind of hit those valence core electrons. And that's where really we'll stop sort of losing electrons. Now, electron affinity is sort of what we think about when we talk about somebody gaining electrons. And this is what we talk about when we talk about anions. Because those guys become more negative because they gained electrons. And this is the energy change that's associated with an addition of an electron in the gas phase. In general, trend is it does increase as you go to the right on the periodic table and up. So it kind of increases both ways. It is not necessarily a perfect trend. But that is the general trend that you see. It sort of increases as you go up and to the right on the periodic table. Remember that electron affinity should not be confused with something like electronegativity that we also talked about when we talked about bonding. Reminder that electronegativity is different, and that's the ability of an atom to attract electrons to itself. And again, it does have a similar trend. It increases as you go up, decreases as you go down. So those are different things. Electronegativity, remember, is what we use when we try to determine bond polarity, right? The difference in how the electrons are going to be shared within a bond. That's like that 0 to 4 sort of number that we had when we looked at bonding. Now, atomic radius is the size of the atom, and it does decrease as you go up and to the right and increases as you go down to the left. We also talked about, again, as somebody loses electrons, the cation is smaller in size than the neutral atom. And if somebody gains electrons, they do gain electrons to sort of their electron cloud. They get larger in size, and that is what happens when we make an anion. And again, all of these trends, as we talked about when I think we did that experiment, atomic size gets smaller, ionization energy increases and decreases this way. We have electron affinity increases this way, decreases this way. We have electronegativity, increases this way and decreases this way. So all of these sort of things together, as we go up and right on the periodic table, as we talked about, we have the overall size is really small, which means they want to hold on to electrons pretty much. They also have very high electron affinity, which means they do hold on to those electrons and actually like to gain electrons. And they have high electronegativity, which means they like to bring electrons to themselves. And again, as we talked about, that's really why our nonmetals typically think about as being negative and gaining electrons. While if we kind of go on the opposite side, we have all these trends for our metals where they're larger, the outer electrons aren't held as tightly, they're a lot easier to remove than nonmetals. They're not looking to gain electrons, and that's why we think about metals sort of losing their electrons and becoming cations in this case. That is also why upper right of the periodic table is the most reactive nonmetal there by fluorine, because it has all those trends of I want to hold on to my electrons, I want your electrons, and why bottom left there of the periodic table is the most reactive metal, because it has all the trends of I'm just going to give away my electrons, go ahead and take them. So that's going to make it much more reactive. Any questions on those periodic trends there? All right. So let's take a look at a couple of these and see which atoms should be larger. Sodium, potassium should be our friend sodium. Yes. And if we look at the periodic table, they're in the same period. Sodium is further to the left, which means it should be larger in that case. Yeah. Which one is larger between lithium and cesium? They also are in the same group. Cesium is further down in the group, which means it's going to be larger, also has a lot more electrons, right, as well to fit in there. So that's going to make it a lot larger. So which one is larger, the hydrogen 1s orbital or the lithium 1s orbital? See, it is the hydrogen 1s orbital, and that is because when we look at hydrogen, +1 charge, right? And lithium +3 charge because it has 3 protons, which means if we look at our 1s orbital, that is like a +1 attraction, right? That is a +3 attraction, larger positive attraction. It's going to actually pull this 1s orbital closer than the same 1s orbital over there. And because the hydrogen doesn't get pushed as close, it will actually be a larger sort of 1s orbital in that sense, because it'll be further away from the nucleus. Any questions on that one there? Which one would be lower in energy? It should be for the same sort of explanation, it actually should be the lithium, right? Again, with that +3 charge, you can actually pull that electron closer to the nucleus, which means because it's closer to the nucleus, it should be lower in energy than the +1 charge of the hydrogen that's not going to pull it in as close. Any questions on that there? All right, so we want to arrange these elements, oxygen, fluorine, and sulfur, increasing ionization energy. So if we look at O, F, and S on the periodic table, it looks something like that. Ionization energy increases as you go up and to the right, which means should be SOF, as we see there. Sulfur should be the lowest, and fluorine should be the highest. And in terms of atomic size, it gets smaller as you go up and to the right. That means actually fluorine is the smallest, and as we go backwards there, sulfur should be the largest in that case. Any questions on that there? Okay, there it is, chapter 11. Any questions on that there? Season here, tier equilibrium. We're going to talk a little bit about some of the parts of this chapter. I'm not going to go into great detail, maybe in all of the parts of it, but we will talk about equilibrium. And let's first just talk about equilibrium in terms of the type of reaction that actually takes place. And the type of reaction that takes place in an equilibrium reaction is a reversible reaction. And a reversible reaction has these two arrows. And the deal with a reversible reaction is there is a forward direction, which goes from reactants to products. So as this reaction, for example, starts, it's going to be like a normal reaction. The reactants are really kind of the only thing, for example, that could be there. And those guys will start reacting and start to make products. And what will happen is as they start making products, at some point, there'll be enough products that they will decide we would like to react with each other, and they're going to head back the other direction. And that is what is referred to the reverse direction, where the products that sort of recombine and actually make the reactants from which they start with. And when it comes to equilibrium, what it really means is, as we'll talk about, is it doesn't necessarily mean that it has the exact same amount of everybody on both sides. It's really talking about the rate of the reaction. And it's really talking about the rate of the forward direction will equal the rate of the reverse direction. And that's really what it means when it reaches chemical equilibrium. When it does so, the result of that is not that you have necessarily equal amounts on both sides, but it will essentially lock everybody into place in terms of their concentrations, in terms of their pressures. If you're dealing with gases, they basically will just stay there. Basically, they'll stay at whatever levels they're at, because just as quick as it goes to the reactant side, it'll go back to the product side and vice versa. So it's going back and forth at the exact same rate, which means if you lose a little, it comes right back and it just kind of stays in terms of their concentration. So that is what is really meant when we talk about something reaching chemical equilibrium. That rate of that forward reaction and the rate of reverse reaction equals each other, kind of locks everybody in place. And the nice thing about that type of reaction is it will be able to maintain that pretty much. It'll just keep maintaining that unless you do something to kind of screw it up, which is kind of the idea of or Le Chatelier's principle that we did the other day in that experiment where we did something that sort of messed it up, the equilibrium. So let's talk about how reactions occur. And reactions occur through sometimes referred to as a collision model. And really, there's kind of two things that does need to happen for a reaction to take place. There does need to be some type of collision between molecules. They do actually have to hit each other sort of in the right place. So not all collisions, just two things coming together, will actually lead to products being formed. They do have to hit each other in the right sort of orientation. And they also have to hit each other with the right amount of energy for a reaction to take place, like that activation energy. I think we talked about in energy, that hill that those reactants have to climb basically to get to the other side. So what happens in a chemical reaction is essentially we're just going to break these bonds and we'll start making some new bonds and we'll make some new guys on our product side, basically. So we have that process occurring, collision, right amount of energy going to initiate, starting to break bonds and making bonds. And that is, if you remember, when we kind of looked at our energy diagram, that kind of hill part right there, this sort of transition state up on top is sort of what we got going on there, where we got something that has some partially broken bonds, some partially made bonds happening. It's sort of right there before we get to our products being formed as it comes back down the energy hill. Now, there's a lot of things that could affect sort of the rate of a reaction, concentration, temperature. When we have a high concentration, for example, when we talk about molarity, which is our moles of solute per liter of solution, for example, remember that it is the solute when you have something like a solution that's really doing the reaction. And if you have a very high concentration of that particular solution, that means you'll have a lot of solute molecules in that solution. And because you have just the presence of a lot of molecules floating around that solution, there's a pretty good chance they're going to come in contact with each other and initiate a reaction taking place. Just like if you had a really small concentration in that solution, you would have a small amount of solute particles, which means it's going to be pretty sparse there. It's going to take a lot longer for them to find each other. It's going to take probably a little slower for that reaction to take place, if it takes place at all, because there's not availability of a lot of molecules basically moving around. Temperature also tends to increase the rate when you increase the temperature. And when you increase the temperature, you're adding a lot more energy, which means, things have a lot more energy. So they're moving around a lot faster. And that's going to lead to probably more collisions that's going to occur. It will also lead to probably collisions where everybody has the right amount of energy, because there's that excess energy that's sort of being supplied by the heat that's being added to that reaction. Opposite is true as well. If you sort of lower the temperature in a reaction, you tend to see it slow down. And that's because everybody loses that energy, right? So now they're moving around a lot slower, and it's going to take longer for them to come in contact with each other. And when they now come in contact with each other, they really don't have as much energy as they did previously. So maybe some of those collisions don't actually lead to products being formed because they don't have the right amount of energy. So typically speaking, if you raise the temperature of a reaction by like 10 degrees Celsius, that's usually enough for a lot of reactions to double how quick it happens. So you can actually double the rate of the reaction by increasing the temperature, something like 10 degrees Celsius. And again, you could put it on ice and the reaction would happen slower. In the lab, that's how you could do it. You could take your test tubes, put it in hot water, right, and increase the temperature, then do the reaction. Or you could take your test tubes, put it in ice and cool it down and remove the temperature aspect of it. And it all has to do with, as I mentioned before, sort of that activation energy, which once again, as we talked about in the energy chapter, is the difference in energy between the reactants and really that hill that the reactants has to climb to get to the other side. At the top here is our transition state, as we talked about. And what we see there is sometimes referred to as a transition state complex. It is sort of an intermediate, if you want to think about it, of something that has partially broken bonds and partially made bonds. And we've talked about it that a lot of times that's very hard to isolate, because very quickly it just really wants to drop down to a lower state of energy and come down the hill, because that's not a really stable situation with partially made bonds, partially broken bonds. And as we can see, that is pretty much the height of energy in this reaction. And things in chemistry are much more stable in a lower energy than a higher energy. So again, it very quickly will sort of come down to the other side. One way we could speed up a rate of reaction is to use a catalyst. And a catalyst is, again, not a reactant. It's not a product. It does not get used up in a chemical reaction. It is usually there just to usually facilitate the reaction occurring faster. And it could do that by finding perhaps a alternative pathway, a more efficient pathway. And I think we might have talked about it as well. But sometimes a lot of times catalysts are written there on the arrow, like platinum or something like that. And sometimes a catalyst could be a solid type of deal. And if you're dealing with, say, gas molecules that are flying around, sometimes the way it sort of works is, instead of those molecules flying around just by themselves trying to find each other, perhaps there's some attraction to the catalyst, and that brings everybody a lot closer together in the same vicinity, and that's going to allow the reaction to sort of to occur a lot quicker than if everybody's just trying to fly around and try to find each other. So ultimately, the way a catalyst speeds up a reaction is by doing this alternative pathway. It's able to find a much lower energy path for the reactants to get to the products. And because the hill that the reactants now have to climb is much smaller, there's probably going to be a greater proportion of molecules that actually can get up and over the hill to the other side. The result of that is we see an increase in the rate of the reaction because much more of them reactants can get to the other side than having to climb, obviously, this bigger hill to get to the other side. Any questions on that there? Now, when we talk about equilibrium, again, as I mentioned before, it is the idea of the rate of the forward reaction and the reverse reaction equaling each other. And as I mentioned, as sometimes misunderstood by people, that they hear the word equilibrium and equal, they automatically assume, oh, we just got equal stuff on both sides, which kind of makes sense in terms of the name. But again, we are talking about here more the rate of that forward direction equaling the rate of that reverse direction. And again, you may not have the exact same amount on each side. So when we look at a reaction like this, and maybe at the beginning you start with 4 and 6 and none of these guys, when this thing reaches equilibrium, you know, maybe you have 2, 3, 1, 4. And when it reaches equilibrium, as I mentioned before, what it's going to be able to do, because of the rates are equal to each other, is basically just maintain those, and they'll be able to maintain what it is, not essentially the same numbers of concentration on each side. Any questions on that there? All right.